Okay. Any questions before we finish up maybe all but one of the reactions for alkenes? So what we have, so what the schedule will be is on Monday and Tuesday that we have class of next week, we're going to talk about alkenes, do problems, and talk specifically Monday about we might have to finish one reaction up and then stereo and regioselectivity, which is what we'll talk about on Monday and Tuesday, as well as doing problems, writing the products and telling whether the reaction is regio or stereo selective. And then when we come back, we're not going to do alkynes. We're going to jump ahead to do free radical halogenation, and then we'll see where we end up with the alkynes at the end. Because I think Dr. Kwan is not going to get to alkynes. And so then everybody can sort of start in the same place next semester. But we'll see. Because our schedule is when we come back, we've got class Monday, Wednesday. Then Friday's the review for the exam on the Monday of the last week of classes, which I'm allowed to do if I put in the syllabus, which I did. So if you're like, you can't have an exam on the last week of classes, yes, if it's in the syllabus. And then on the Wednesday and Friday, we'll have sort of whatever review. I do have a number of multiple choice questions to review for the final exam that I will release or that we'll do in class, or we'll answer questions, or we'll see where we're at. We should be in plenty of. We shouldn't have to rush through anything, and this isn't really rushing because we could go faster if we wanted to. Okay. Any questions?
So do you have an exam before the final exam?
Exam number 3. It's Monday. It's the Monday, yeah, the 9th of December. That's exam 3. All right. Okay. All right, so we have a couple more reactions to talk about. We have 2 more additions to alkenes, and then we've got a cleavage reaction where we're going to break the alkene apart, which we'll talk about after the first reaction. So the first one for today is SIS Hydroxylation. And so SIS Hydroxylation means that I'm adding 2 OHs to the double bond, 100% cis. So for this SIS Hydroxylation reaction, there'll be 2 reagents I can use. I'm going to add 2 OHs. It's going to be neither Markovnikov or anti-Markovnikov, since I'm adding the same thing to the double bond. And it will be 100% cis, as the name says. So the question is, what reagent do I use for this? And then I will show you a mechanism that hopefully will help you remember or explain why it's 100% cis. But it's not a mechanism that I will ask you to do on the exam. And next week I will probably create a chart as well of the alkene reactions, as well as which ones the mechanism would be relevant for and which one it's not. Because I actually have that table and that list that I'll put up at some point. Okay. So here's my double bond. And what I'm going to do is I'm going to add KMNO4 in basic conditions. So KMNO4 with hydroxide will end up adding 2 OHs to the double bond. So I'll end up with an OH on the first carbon, an OH on the second carbon, and they will be 100% cis. And I'll just write it this way because you're like, that's trans. No, it's nothing. Because this is an acyclic compound, so there's free rotation. But I'm going to add 2 OHs, 100% cis, so when we do a ring, we'll have to put our bold and dashed wedges in. Okay, so this is KMNO4 and base. There will be KMNO4 and acid in a minute. Sometimes the books will write this as cold KMNO4, KMNO4 with no base, but I put the base in. Part of the reason for that is if you're trying to remember the KMNO4 reactions, KMNO4 with hydroxide add 2 hydroxides. That's what it adds. KMNO4 and acid is going to do something else. So that's what it's going to add is 2 OHs. Now the question is, why is the reaction cis? Number one, it's not anti-Markovnikov. It's not Markovnikov because I'm adding the same thing to the double bond. And that's going to lead us to talk about regioselectivity probably on Monday. So if I look at this, let's do this reaction with a ring. So when I add KMNO4 and base to the ring, it's the permanganate ion that is the most important thing here. And I'll write it a little bit different than I did earlier, and this is more consistent with the notes and the video that I have online, but it really doesn't matter. Manganese, the permanganate ion looks like that. Whether I have the O- pointed towards a double bond or not is kind of irrelevant. So what will happen in this case is the following. I can take this pair of electrons and I can move it to form a carbon-oxygen bond. And at the same time, take the double bond and move its pair of electrons to form the top carbon-oxygen bond. And then this pair of electrons goes into the manganese. Okay. And so if I look at the molecule that way, well, first of all, the manganese is gaining electrons. So in the general chemistry sense, the manganese is gaining electrons. That means it's undergoing reduction. The double bond, on the other hand, would then be undergoing oxidation, which if I'm adding oxygens to a double bond, that's our basic definition of oxidation. But this one, it's easy to see from the electron's point of view exactly how the manganese is undergoing reduction. And then we also have to talk about oxidation numbers on carbon, and that is also undergoing oxidation there as well. So what I end up doing is I end up forming a 5-membered ring from the oxygen that's attached to the manganese, and also then the 2 oxygens I added to the double bond have to be added cis. And the reason that they have to be added cis is because this 5-membered ring that I'm forming here is not big enough to add 1 oxygen to the top face and add the other oxygen to the bottom face. So a 5-membered ring is not big enough to add to top and bottom that would give me the trans product. The 5-membered ring is only big enough to either add to the top both or add both to the bottom. If it was a 6-membered ring, then we could add 1 top and 1 bottom, but it's not. It's a 5-membered ring. So in terms of our shapes, what do we have? We have the triangle is always 100% trans. The square is cis, and now this 5-membered ring is also cis. And we won't have a 6-membered ring. That could be either cis or trans. So in this case, the 5-membered ring leads us to add exclusively cis. Whether it's a bold dash or a dashed wedge, doesn't matter. It's going to be cis. So I've added the 2 oxygens then to the double bond, cis. Okay. And that's what I'm showing you here to kind of help you remember, okay, permanganate's always going to add 2 OHs, 100% cis. Then what happens is then the hydroxide comes in, and it's going to cleave off the manganese, so that what I'm going to end up with is I'm going to end up with then two OHs that are cis because the manganese added the two O's cis. And then what I will also end up with is manganese dioxide, which is a brown precipitate. And in lab next semester, we're going to be taking potassium permanganate, which in general chem, whenever you did a titration with the purple solution, the potassium permanganate, you did a titration of iron, I believe, with that. So in this case, the purple solution gives a brown precipitate. And next semester, we're going to do the same reaction, and then we're going to have to get rid of the brown precipitate by filtering through a C light pad, just like we did to yeast. So, and I'll come back to that color change because that's actually can be used as a test for a double bond. So overall then we end up adding two OHs cis with the permanganate. So it's got to be potassium permanganate, cold, or with hydroxide. The textbooks use different conditions. I will give you the hydroxides. The book may not. So if you see the book saying cold, they intend that it's OH minus. If they say hot, then most likely they mean acidic conditions, which is a completely different reaction. Okay. Right.
I don't understand how you got those two OHs. How did you turn the oxygen?
That is part of the mechanism that we wouldn't talk about. So what's going to happen is that basically those hydroxides are going to attack the manganese and make it leave. So that's an inorganic reaction, and since this is organic, we're going to skip that part. So all the hydroxide does is it just basically breaks those two bonds and leaves two OHs behind. Okay. For some of these mechanisms, the inorganic part we're not going to talk about. So if both of these steps were doable, then it would be a mechanism I could ask you on the exam. I cannot ask you this one for that reason. Okay. It's kind of like, how did the hydrogen replace the mercury? That's an inorganic reaction that we didn't talk about. Okay. But the reason I'm showing you this is the key part. Why are they adding cis? Because the permanganate has to add them cis in order to form the 5-membered ring. Okay. Right. So that's the first way to make a cis, or to make the SIS hydroxylation.
What would all of the products be, since wouldn't there still be an extra two?
There would be all sorts of stuff in there.
Okay.
But one of the things we would see is the permanganate. So there would be hydroxides in there. There would be other things in there. But for most of these reactions, what I'm mostly interested in is what's the final organic product. Not everything else is in there. Because if you think about hydroboration oxidation, we added the borane, and then we turned the boron into an OH. What was in that mixture? A whole bunch of boron attached to oxygen stuff that we don't worry about. So we're only really concerned about the fact that those two O's are cis because they were added cis to begin with. The rest of the mechanism, you're just going to have to accept. So permanganate, this is an easy reaction to do simply because permanganate is cheap. And you just have to basically do it under basic conditions or do it cold. And permanganate is an oxidizing reagent, meaning that it does add oxygen to things. So you use it in general chem lab. If you go to the pet store, you can get potassium permanganate in a bottle to add to aquariums, because when your aquarium gets super cloudy, you can add potassium permanganate to it in a low enough concentration where it doesn't kill the live things. But what it does is it takes all the insoluble cloudiness, which is all organics and waste and stuff, and what it does is it puts oxygens and OH groups on them, making them water soluble, and magically your water clears up because now all that insoluble cloudiness is now soluble. So if you've ever had an aquarium, then if you put the drops in, you'll see it's just potassium permanganate that's purple, and it doesn't kill the fish, allegedly. So that's where it's used. You can actually go to the store and buy it. But that's what it's going to do with double bonds. So the other reaction that you can do for SIS hydroxylation is a little bit more expensive. And that's to use osmium tetroxide and hydrogen peroxide. And this mechanism is basically the same, only in this case, the osmium is one of those transition lanthanide metals that costs a fortune. So what we can't do is we cannot do this reaction 1-to-1 mole equivalent of osmium to double bond because that's too expensive for us to run. But the mechanism is the same. So in other words, if I reacted the osmium tetroxide with this double bond, I would make exactly the same product that I did before. I would add OHs to each of the carbons, and they would add 100% cis. If I take my same alkene of the cyclohexene, osmium tetroxide has this structure. So it has OSO4 with double bonds. That looks almost identical to the potassium permanganate. So the arrows would go in the exact same direction. I would take this pair of electrons to form the O carbon bond, take the double bond of the carbon to form the other carbon-oxygen bond, and a pair of electrons would go back to the osmium, so it is being reduced. Okay. And then the osmium, because again it's going to form a 5-membered ring, must add the 2 O's from the top face or from the bottom face, but it has to add them again 100% cis. So the difficulty here is the cost of osmium. I can't do this 1 mole. I can't do 1 mole to 1 mole because it's just too expensive. So what happens is that not only does the hydrogen peroxide, when I add it to the second step by a mechanism that we're not going to talk about, but basically the peroxide is going to strip off the osmium. It's going to leave behind now the cis dialcohol, but it's going to reoxidize the osmium into osmium tetroxide. So that a little bit of osmium is going to be catalytic in terms of adding to the double bond. Then when it gets stripped off, it gets converted back to osmium to add to another double bond. And so it's constantly in a catalytic cycle. So you can use a fraction of a mole of osmium to get this reaction to go. So that's the difference there, is that it's just a different set of reagents, but it does the same thing by a nearly identical mechanism. So that's SIS hydroxylation, either KMNO4 and base or osmium tetroxide and peroxide. So one of the things as you're, making a table of reactions, you're going to see peroxide in different reactions. So you just have to remember where the peroxide goes. Because peroxide, if you just say peroxide adds 2 OHs cis, Yes. But what else does peroxide do? Right? It can react in the other additions as well. And so we just have to be careful with peroxide that it will do multiple reactions. Okay. And I guess what's the other reaction it'll do? We'll get to that on Monday, because it'll be involved in another reaction. Okay, so this is cis hydroxylation. Not Markovnikov, not anti-Markovnikov, just 100% cis. Is that kind of clear? So not a mechanism I would ask you to do, but if you can associate that mechanism, if you remember it, then you can remember that two OHs get added cis. Okay. The next reaction is not an addition, it's a cleavage. So this reaction is called oxidative cleavage. So oxidative cleavage is exactly what it says. I mean, a lot of these reactions, there's very little creativity when it comes to naming reactions that aren't named for a person. So cis hydroxylation, two OHs cis. Oxidative cleavage, I'm adding oxygen and I'm cleaving the double bond. So there are multiple ways to do oxidative cleavage. And so if I take that same, well, actually I'm going to change the double bond here into this one to start with. So if I take this double bond and I'm going to cleave it, the reagent that I'm going to use is KMNO4, now with acid, and sometimes you'll see heat as the reagent as well. So I'm going to take KMNO4 and add acid and heat. That cleaves the double bond. So what I'm going to end up doing is I'm going to end up cleaving this double bond so that I can write the molecule without the carbon-carbon bond. And I'm going to end up adding oxygens to those two carbons in the form of carbonyls. So I'm going to end up converting the two CC bonds or two carbons in the carbon-carbon double bond into two CO, bless you, double bonds, two carbonyls. So you erase the double bond and write two CO double bonds to the carbons that were in the double bond to begin with. However, what I need to talk about here before we go any further is the sort of oxidation scheme that you can have for aldehydes, which means I have to go all the way back to the beginning, which is a primary alcohol. So a primary alcohol is one where the OH is attached to a primary carbon. And if we oxidize a primary alcohol, the first thing that we can get is the aldehyde. So if you look at that, you'd say, okay, yeah, I get that's oxidation because I've lost two hydrogens. And so loss of hydrogen is oxidation, just like gain of oxygen is oxidation. So you can convert a primary alcohol to an aldehyde, and we'll talk about methods to do that next semester. But then an aldehyde can be oxidized up to a carboxylic acid. And that's going to involve the addition then of the additional oxygen. So the scheme for aldehydes, carboxylic acids, and primary alcohols is that primary alcohols can be oxidized to aldehydes, which can also be oxidized up to their highest form, which is carboxylic acids. Okay. And I guess to relate this to That's a number of things. Number one, you don't drink methanol unless you want to go blind or die, one of the two. Because methanol is wood alcohol. But the reason why methanol is toxic, because in its oxidation scheme, you would take the one carbon and convert it to formaldehyde, and the only thing formaldehyde should be in is dead, or the only thing formaldehyde should be associated with is dead things, because that's what we preserve them for. So if you drink methanol, you're going to make some formaldehyde, which is only good once you're gone. In winemaking, like we did our fermentation, so we took our fermentation, we converted the sucrose into ethanol. The reason we had to have the little device that let the CO2 gas burp out but not let oxygen in is because when you're doing fermentation and you want grain alcohol, which is ethanol, you want that versus having the ethanol oxidized to acetic acid or acetaldehyde, which would not be good to drink or smell or anything like that. So, if you have some super old bottle of wine that you're going to celebrate drinking and it's gotten oxygen into it, it might be you're going to drink some vinegar as opposed to alcohol, because vinegar is acetic acid. So this oxidation scheme is important from that standpoint. Anything that's an aldehyde can react with oxygen gas and get converted to a carboxylic acid very easily. So, and carboxylic acids tend to reek in terms of their smell. They are named after, well, the 4-carbon acid is named butyric acid after rancid butter. So, butyric acid, next semester when we make our esters, we will not be using butyric acid as far as I know. But some of the other ones, those acids have an unpleasant smell. Aldehydes are okay, but once the aldehydes get oxidized, it changes the fragrance. Primary alcohols are typically oxidized all the way to carboxylic acids, using things like peroxide and KMNO4. The KMNO4 part being important here. Aldehydes also tend to be oxidized with peroxide and potassium permanganate as well. So the reason that I have to show this is because I just cleaved the double bond and I made aldehydes, but my aldehydes are now in the presence of KMNO4. So what is the KMNO4 going to do to those aldehydes? It's going to oxidize them into carboxylic acids. And so the final products of these reactions, of this reaction, is going to be 2 carboxylic acids. Okay. So when we're looking at doing cleavage, the first thing we do is erase the double bond, put 2 carbonyls in place. But the second step then with KMNO4 and acid is to convert any aldehydes into carboxylic acids. Okay. So those are the final products for KMNO4 and acid. And the reason that the aldehydes get converted to carboxylic acids is because this is the oxidation scheme for primary alcohols, aldehydes, into carboxylic acids. Mary?
Can you please go back over the steps that you just listed again?
So the first step is, step number 1 is going to be erase the double bond and replace the carbon-carbon double bond with 2 carbon-oxygen double bonds. And we'll do a couple more problems here, so we'll take it. That's step 1. Then step 2 is for any aldehydes that we make, they get converted to carboxylic acids. So if you want, we can just insert an oxygen between the carbon and the hydrogen here. So those are the 2 distinct steps that we use for oxidative cleavage. So in this case, because they both became aldehydes, they both would then, the final products would be carboxylic acids. And if you're creative, you might say, well, why don't you just use 1 mole equivalent of KMNO4 so that you don't have any excess lying around? It doesn't work that way, because you always have to have excess KMNO4. And even if I convert some of the aldehyde to carboxylic acid, I'm going to take all of them to carboxylic acids. So let's do another molecule here. Let's say I had this double bond. And I'll just make this one an ethyl group just for fun. So if I had this as my alkene, and I said, what are the products using KMNO4 and acid? We would have cleavage. So what we would do is we'll write the molecule without the double bonds in place. So I erase the double bond. I'm now going to replace the carbon-oxygen, or the carbon-carbon double bond with carbonyls. The molecule on the left is a ketone. It's done. It's a ketone. I don't do anything to ketones. But the molecule on the right is an aldehyde, and so it would be converted to a carboxylic acid. And so the carboxylic acid and the ketone would be the final products.
Shouldn't it be CH3 say CH3?
Typo. Just shows stuck with 2 CH3s. So that's how we would do those 2 steps. All right, everybody kind of with me? So erase the double bond, convert everything to carbon-oxygen double bonds, and then if there's any aldehydes, oxidize those to carboxylic acids. Now, what would happen if the double bond's at the end of a chain? If the double bond was at the end of a chain, there's only one small modification that I would make. So let's say I was reacting 1-butene here with my KMNO4. I'm still going to cleave the double bond. The carbon group on the left would start out as an aldehyde, right? And then the carbon group on the right would actually end up looking like that initially. So all I did was, again, erase the double bond and put in 2 carbonyls. This molecule, when I talked about formaldehyde is let's spell it correctly. Formaldehyde. So formaldehyde is the 1-carbon aldehyde. Okay. So that's what, there's different places you find formaldehyde. Like I said, usually dead biological samples are stored in formaldehyde. I believe they use methanol in the biology department because they got rid of all the formaldehyde when we moved from the building that's now a parking lot to over here a long time ago. And they just now use methanol. But formaldehyde still shows up. I mean, you can use it to preserve dead things. You can, sometimes formaldehyde's an environmental issue because formaldehyde's used in making plastics and fibers. So I think part of the new car smell might be a little formaldehyde. But there's detectors you can go around to new construction, new carpet, and make sure there's no formaldehyde gas that's, you know, coming out of there. Because in general, dead things should have formaldehyde and living things shouldn't. But I digress. So, step one. KMNO4 then is going to convert this aldehyde on the left to a carboxylic acid. That we've done. What happens to the formaldehyde? The formaldehyde actually then gets converted to that which is carbonic acid. Carbonic acid, as I take a sip of my carbonic acid, breaks down into carbon dioxide and water. So the carbonic acid then becomes CO2 and water, because carbonic acid for the most part is unstable. Those are the two final products.
I don't understand how we get from the formaldehyde to the carbonic acid.
Because the KMNO4, if you think of each one of these hydrogens as being like an aldehyde part, it's going to basically insert an oxygen between the carbon and the hydrogen. Since there's two of those, it's going to insert an oxygen into both of them. We could write like an oxidation scheme there where you add one oxygen, which would form formic acid, and then there would be another oxygen forming carbonic. The KMNO4 just takes it all the way to the carbonic acid. And then the carbonic acid breaks down to form CO2 and water. Now, what's the relevance of this? The relevance of this is that next semester in lab, we're going to talk about spectroscopy for a good chunk of the first few weeks. Spectroscopy is what we use to determine the structure of a molecule. Zaitsev, Markovnikov, they didn't have the luxury of spectroscopy. How did Zaitsev know that he formed the most stable double bond? I don't know, because the way he did it, I would never do it that way. So somehow you have to figure out what the structure of the molecule. If Zaitsev had really done what we give him credit for, he would have had to figure out where to put the chlorine to which carbon. So nowadays, 15 minutes, pretty much you can give me most anything, and I can probably figure out what it is using a technique called NMR that we'll talk about next semester. IR is powerful for certain things, and we'll talk about that, but not as powerful as NMR. But those only existed from the 1950s on. So before 1950, how did you determine what functional group you had in the molecule? You had to use color tests. And so, for instance, bromine is a red liquid. If I think I have a double bond, I add a drop of red bromine to my solution. If it instantly turns clear, the bromine reacted with something. What did it react with? A double bond, adding 2 BRs, 100% trans. But the bromine color would disappear. If the bromine color persisted, no double bond present. Of course, triple bonds will do the same thing, so it's just a test for double or triple bonds. KMNO4, purple color, put it in with double bond, you will see a brown precipitate form. That's an indication of the double bond forming, or the double bond in your molecule. All right, I got a double bond from my 2 color tests. Is the double bond at the end of the chain or is it in the middle? I could use this test, and then if I see a fizz, the double bond's at the end. If I don't see a fizz, the double bond isn't at the end. The chances are the double bond's in the middle of the molecule because there's only 2 ends. But these color tests are what we could use to determine what functional groups that we have in the molecule. Think you have an alcohol, add a small drop of, or had a small sliver of sodium metal to it. If it fizzes the same way that sodium metal fizzes when you add water to it, only less violently, then you know there's an alcohol in there. So there's all these color tests. I could tell you, this is sort of I went to school, walked to school in 10 feet of snow, no shoes, both ways, right? If that's still a common thing that old people tell you, when it's like back in my day, well, when I took organic chemistry lab second semester, our entire second half of the second semester, they handed us 4 test tubes and said, figure out what they are. Yeah, it wasn't 4 hours a week. It was like any time you had time, you were getting the key to go in the lab to figure out what was going on, which I guess they trust us not to blow up the lab, but it was no fun. Because now these color tests have pretty much been supplanted by one infrared instrument that we'll learn about next semester. So the color tests are what we use pre-instruments. So that's why I'm showing you kind of the physical properties, so you get a sense that you could still use these tests for that. So that's what happens with double bonds that are not in rings. So then the question is, what happens if the double bond's in a ring? So let's take this methyl cyclohexene and let's react it with KMNO4 and acid. Now, first of all, when the alkene is in a ring, even when I erase the double bond, I still only get one molecule because the rest of the ring is holding it together. If you get 2 molecules, then it wasn't in a ring. The reason I stress that is because every textbook likes to give you the oxidation products and say, what was the alkene that you used to make these? So in other words, they'll say, I got CO2 and water, and I got this carboxylic acid. What was the original alkene that I had before KMNO4 oxidation? And that was another technique that people used to figure out what their double bond was that they cleaved it into 2 parts and then figured what the 2 parts were, using color tests and other things. So in this case, if I cleave the double bond, I'm going to end up with 1 molecule, with 2 carbonyls. So cleave the double bond. You can, on an exam, if I ask you to do this, and I probably will, there's no probably part of this, I will. So you would erase the double bond, put 2 carbonyls in place. So now I have a ketone on top and I've got an aldehyde on the bottom. The KMNO4 is going to convert the aldehyde part into the carboxylic acid, so that's going to be my final product. So the reason I'm putting it in this form is so that you can kind of see what happened to the double bond. Now, in general, if it's going to be a problem from Top Hat, they're probably not going to put it in this form. They're going to stretch it out linearly. So how do you do that? Well, let's choose an end. End. 1, 2, 3, 4, 5, 6. I've got 7 carbons in that chain. When you're first starting out, it's always good to number those so that you don't gain or lose any carbons along the way. So that means I have a 7 carbon chain. 1, 2, 3, 4, 5, 6, 7. So there's 1, 2, 3, 4, 5, 6, and 7. So what's carbon 1? Carbon 1 is a CH3. What's carbon 2? A ketone. What's carbons 3, 4, 5, and 6? They're all CH2 groups. And what's carbon 7? the carboxylic acid. So if you have to stretch and unravel a molecule, it's always best to put numbers to the carbons, because that will let you know how many carbons are going to be in the chain and what goes where. And then if they're really evil about this, what they'll do is they'll just give you a list of names. Right? So that this would be 2-oxo-heptanoic acid. Number one, I named it this morning. But if you're like, oh, we're getting close to the final, so naming will be part of the final. You'll still get the sheet, but you still have to remember how to do it. So that's what happens with a ring. The ring gets cleaved, but it still stays together. Unless there were multiple double bonds in the ring, at which point you would cleave those pieces apart. So if you have a molecule like this and they say, what was the original molecule? Number one, if you just see one molecule, it was a ring. And you're going to join the two carbonyls together. And if it's KMNO4, that carboxylic acid wasn't a carboxylic acid to begin with. It was an H of an aldehyde. So they love to ask those problems working backwards. And the reality for that is because that's the way people had to determine the structures, was they had to break these apart and then determine the individual parts and then put it back together again. And I'll give you one other example here. Okay. So this is just oxidative cleavage with KMNO4 and acid. It's not really the most popular kind, but it's certainly the cheapest. The other way to do this reaction, and we'll use this molecule that I had before, only I'm just going to leave them as methyl groups, is to use what's called ozonolysis. So ozonolysis, lysis means cleavage by ozone, or cleavage of ozone, cleavage with ozone, ozonolysis. Ozone is O3. And without going into the full-blown mechanism, ozonolysis is a little more flexible in the fact that if I do ozonolysis with H2O2, I'm going to cleave my double bond and convert each one of the carbons that were in the double bond into carbonyls. Going back to what I said earlier, aldehydes can be oxidized to carboxylic acids with KMNO4 and peroxide. So the H2O2 would oxidize that aldehyde into a carboxylic acid so that the final product would be the ketone and the carboxylic acid. If I use ozone and H2O2. Okay. But what if I don't use H2O2? What if I want to keep the aldehyde? Ozonolysis will let me do that. Then I just use ozone with R2S. And R2S is the sulfur equivalent of an ether. It will not oxidize the aldehyde, so what happens is any aldehydes that I form after my cleavage will stay. They will not be oxidized. So ozonolysis is a little bit more forgiving in it's a little bit, you have more choices. You want to keep the aldehyde? Use R2S. You want to oxidize the aldehyde? Use hydrogen peroxide. So the ozone allows us to go in either direction. Right? And so let's see. Ozone. What do we know about ozone? Ozone way up in the atmosphere, good. Right? It blocks the UV. It reacts with the UV light that comes in so that we don't have the kind of UV light that basically would burn our skin off. We're not talking suntans here. We're talking about flesh burning UV rays, UVC, right? And some UVB. Ozone at the ground level, if you live in Cleveland or any big city that has ozone action days, they'll say, today's an ozone action day. Don't go outside. Don't, drive your car. Don't cut your grass. Don't fill up your car with gasoline. All of that will react with sunlight and will make ground level ozone. Ground level ozone loves double bonds, just like this. Double bonds that might be in my lungs, double bonds that's in the tires of my car, double bonds that are in any kind of plastic or rubber material. And so over time, ozone will destroy those materials because it will cleave the double bonds. Another good source of ozone, photocopiers. Although I haven't put anything rubber next to a photocopier to have it get destroyed, but over time it will. Okay. All right, so on Monday what we will do is we will finish up with HBR anti-Markovnikov edition, and we'll start talking about regio and stereoselective, which we will finish up on Tuesday. Okay. Any questions? Put them up on Piazza over the weekend, and I will answer them